Hello, can you hear me? You can hear me, right? I'm assuming you can. So this week's lectures were on contrastive learning and vision language models, right? Let's just review contrastive learning, concept of contrastive learning. So how is a contrastive learning objective defined and like different from say like cross entropy loss? So in the case of cross entropy loss, we usually have a sample and its corresponding label in supervised learning setting. Um, like say we have an image of a dog and its label is dog and those kind of things, and then yeah, we train a network so that it improves the score for its correct class. So that's how it is, right? So differing from that objective, uh, so there we are trying to learn a hyperplane that separates two classes or something like that. Here, the how it is posed is that similar looking things or samples of same object should be closer to one another, while samples from different objects or different images should be farther away. So we're trying to model a metric space, so where these distance rules are followed. Like I think the first time how it was, so it is usually defined between a pair of images, not just one image. So you need multiple sample points to compute this objective and optimize the network. So suppose we have two samples, say xi, xj, and say they belong to the same class. Say both of them are. So there are two cases, right? One case is where both xi and xj belong to the same class, and another case. So in such a case, let's say the label like say it's, same class, that meaning what do you say, yi is equal to yj in that case, right? So this is one case, and then there's another case where xi and xj belong to different classes. So yi is not equal to yj. So how do we come up with a distance objective to make these two close and these two far away? Like in this case, in case 1, we want what, xi and xj should be close in our feature space. Here we want xi and xj to be far away. right? So what do? We compute that. Let's just so say we have the sample xi, we pass it through a network f, and then we have got its features f of xi. Similarly, xj we pass it to the feature extractor, and we got f of xj. So these two are in the features of them. In the feature space, we want to optimize the network so that the features of xi and xj would be close, and xj and xj would be far away if they belong to different classes. So the objective would be, so it takes both the input samples images xi and xj, and so there are two cases, right? First case is when yi is equal to yj. So when yi is equal to yj, what do I want to do? I want to bring xi and xj close. So we can compute the distance between the two features, f of xi minus f of xj. So we want to minimize this, as this is a loss function and we want to minimize it. So this is the distance, right? The distance between both the features. yi is not equal to yj minus of f of xi minus f of xj square. So here, when I am minimizing this term, I am eventually equivalently maximizing the distance between both the features. So why is this kind of learning advantageous or preferred than learning using, say, cross entropy loss? Like, can you name an application where I would say maybe like learning the distance based things could be probably an easier or more open way of learning the feature extractor rather than using cross entropy loss? So suppose we know the number of classes beforehand, and it's just like, I have 10 animals, I want to classify between 10 of them. Then I can just add a simple linear layer and then train using softmax cross entropy loss, right? But I can also do it this way, like this contrastive objective. So but then in which cases can this be more useful, even if it's a classification task? If the number of classes are too huge, yeah, right. So how much is huge? We do normally 1000 classes, right? In ImageNet we do learn 1000 class classifier, which is a very common problem. So one of the early tasks where this objective was proposed, like some sort of contrastive objective was proposed and used, was actually face recognition task. So there, in face, so here, when we try and learn, so by doing this contrastive objective, what are we making at the end? So it turns out, how would our feature space look like? So similar samples belonging to one class would be clustered at one place, and if it's anything else, it would be somewhere far away, right? Say this will be class 1 and this is class 2, and then this will be class 3. So you're learning this kind of sort of clusters, and if there's anything new that comes, if it does not belong to any one of them, it can show up as some other at some other far off place, right? So by explicitly making these far away using this distance metric, it can be used in face recognition easily, because when there is a new face, that is, so initially say I have a database of say 100 people. Of say 100 people. So yeah, I train. So if I have 100 people and I say I have some 10 images per person, so 10 images per person, making it like 1000 samples of data set, and can be supervised learning, because I have labels for each of these 10. I have one ID associated with them. I could learn a normal classifier, and in such case it would even if there's a test sample belonging to one of these people, it would rightly classify. But suppose when there is a new person, and I just learn using normal CE so it would tend to project it to somewhere in this space which is present occupied by all these 100 people. It is not necessary that it puts it somewhere far away as such. But when we train it using these clustering objectives, this like some contrastive learning, because here what it is trying to do is bring the classes together, like one samples from one class together, and it takes help from the other classes samples as well, right? Because the objective has two samples in it. So when it takes something as positive, so by the term positive we mean something that belongs to the same class, right? In the supervised setting, so positive, and it treats all the other classes as negatives. Because it treats all the other classes as negatives, it tries to push them away, right? Like all the other classes. So even if there is some new class that comes up, so that new class will get placed somewhere far away from any of these clusters, because it knows it's different from what is existing currently, right? So in such a case we could use some threshold for based on mm, oh yeah, if we learn using this contrastive loss, we do not have a classifier layer as such, right? To compare when we get a new test feature. So in such a case, so testing is usually done using either nearest neighbor, by storing your training image features, or nearest Android classifier. That is, you use the training samples to compute the class centroids for each of the known classes, and then use them as the classifier. So what would that mean, nearest centroid? So this is very useful and used whenever there are very less number of samples, right? Rather than learning something, this simply using nearest centroid classifier is proven to be very effective. So here, how would I define my classifier? So as I said, there are 10 images per person, right? So if I have to say Ci is my classifier vector, like the representative feature vector, it would be summation of all yi is equal to I, indicator of all this samples, f of xi 1 by summation of indicator of yi is equal to 1. So these would be the class centroids. And when I have a test during testing, so after training we can compute this. During testing, so I have a test sample xt, I pass it through the feature extractor, and I would get f of xt then I compute the distance. So, or like I can write the prediction y cap of t is equal to argmin of I belonging to 1 to 100, no? 100 classes I said here, of f of xt minus ci. So whichever it is closest to, it would be classified into that. Or before this, so this is if we are assuming that all the test samples come from the 100 samples only. So xt belongs to one of the seen 100 classes. But then suppose xt can come from new class, that is if there are new people like which are not in the database, out of the database. So if there's a new person coming, in such a case I can compute what this distance is, that is the minimum distance is minimum over I norm f of xt minus ci whole square if this distance is greater than some threshold. If this is greater than some threshold, which that threshold in that threshold can be computed in some heuristic way. If it is greater than some threshold, that means it is far from all the existing centroids, right? All the existing centroids, and we call, and we can say that this yt belongs to a new sample, or name it like yt is 101 because it's another class you can add. So and once you do this, you can add it to the database as well. That means you can calculate C101 as f of xt because that's the only feature, right? So next time if there is another sample that comes in, you can compute its distance with respect to C. If this becomes the closest one, then you can update the C101 using the new samples. Does that make sense? Okay. Yeah, while writing this, I had this question. So I said greater than some threshold, right? Some threshold tau. So how to set tau? So you already have all these clusters. That means for all these 1000 samples, you know where they are, how the centroids are. That much information you have after training. Now suppose you have to set this threshold to identify whether it doesn't belong to any of them and find the to be able to label this sample, right? To label this as new based on the threshold. So empirically, how would you set threshold? In a logical way, if you have to come up and design a threshold there, what would you do? A very simple logic. If you had to use, what would you define it as? You have all those centroids. So based on that, what would you do? Come on, if this was a question in your exam, what would you write? See, just using the centroids, suppose. We're calculating. So how are we even finding this? We're finding the distance, right? Distance of how far it is from a centroid. If it is greater than some threshold. So how do I define this threshold? Take threshold as maximum interclass distance. Yes, yes, correct. Yeah, that's exactly what I was thinking. So threshold can be defined as max of Ci minus Cj, where I comma j belongs to 1 to 100. So take all the pairs, compute the distance between them, and yeah, you know the interclass distances, and set it as max of them, or max plus some small delta with it. That delta can be a very something you manually set. But yeah, if it is farther than the distance between any cluster, then it's probably a new one, right? It doesn't belong to any of them. It indicates that. So you can use that threshold. So learning this kind of metric space, yeah, can lead to more interpretable representations, and in this kind of open set scenario where new things can come up. Can you give some intuition on why this works? Yeah, so like my understanding of why especially in the supervised setting, why this would work differently is that suppose like when I so if it is just about these 100 people, if I care only about them, then I would say it becomes sort of how well you tune empirically, try out different loss functions, different models, and something has to work. It would practically become just that. This is one of those ideas where one could try. But beyond that, why it would be useful is, see, even in when we are learning a classifier, so what is the aim of that? So that geometrically, if you have to imagine how this two would be different, that is using cross entropy loss versus contrastive loss. Bottom line, it's a very empirical thing, but still this is my intuition. So yeah, like suppose in CE loss, what would we care? We care about separating two classes, right? That is what you're learning, a hyperplane, and based on similarity with that, like a sample either belongs to this side of the hyperplane or the other side of the hyperplane, right? And then you're done. So that is all you care about. You do not care about whether they are all close to each other or not, because the objective is to learn a hyperplane, and it learns a hyperplane. So when I have a new sample, like which does not belong to the known classes, it would project it somewhere in this space. It could be anywhere for that matter. And it could be close to one of these existing samples as well, right? Like we don't know for sure. We've not done anything to make sure that that can be far away from any of the scene. But in contrastive loss, that's not how we are defining the objective. The objective is more like, so the samples, once you learn them, it would be something like all these class 1 samples, because there is no classifier. So I have learned this cluster, and then I have learned another cluster. So what you are learning is this cluster and these new clusters. So and the hyperplane becomes a function of this cluster. Here it's not that way. As in, so I can then define a classifier, right? Like this is C1, this would be C2, then this would be C3, and then based on these distances C1 and C2, you construct a hyperplane. You make this becomes your decision boundary, but that decision boundary is a consequence of how the features are clustered. But here you are only learning the hyperplane, and all you care is about separating them. So here the objective is more about separating them. Here it's about clustering. So this is my intuition of how these two differ. Although at the end it's all about classification. So does that make sense to you? Yeah, as I said, it was initially proposed and used in face recognition tasks. So there was this paper called FaceNet. It came, I think, in 2014 or 15, something in that time, where they proposed this called as triplet loss, which also is a distance-based objective. So what they do is, so they have an anchor, and they have a positive. For each sample they define two things. One is a positive, and another is a negative. So what they try to do is they make bring the anchor close to its positive and push apart the anchor with it and its negative. And by what extent you do it, that is again they define a small epsilon for it. So what would happen, like eventually when you after learning, this would become like, so the anchor and positive would be like clustered together, and the negative would become further apart. So by choosing these anchors, so at every step I might be choosing different positives, negatives and all that, right? And I would be choosing this for each sample. Here it's just one example which I'm demonstrating. There might be some other, for another example also I would be doing all this. So eventually after learning, they end up becoming clusters. It turns out to be a clustering objective. So what do I want to do? I want to minimize the distance between anchor and its positive. Minimize the distance between anchor and its positive. So at every term loss objective, it has two things, right? Anchor, its positive, and its negative. So this minus, so this is this distance I want to minimize, and I want to maximize the distance between anchor and its negative. And I want this distance to be greater than epsilon at least. So I have this epsilon term. So as long as this term is greater than 0, I have this objective. That is my target. So this is like the margin function, max of this comma this. So when would this be active? When would this term be active? When would 0 be active? Let's see. So can you tell me when does this? So it has two options, right? So when does it become 0? So what is the condition for this term to become 0? You should infer it from the equation itself. Distance between positive and negative terms is equal to alpha. Not equal to distance between uh, pos- positive and po- so if the negative is farther away than the positive by distance epsilon, that means what I want in distance space is something like uh, so this distance. So when does this term, I have no, there are two options for this loss, one is 0 and one is this whole equation here. When does it become 0 is my question. So let's say this is d plus and this is d minus, so this is d plus, right, and then this term is d minus. So when does it become 0? Max of this is 0 when d is greater. What d? When d minus is greater. D greater meaning what? Greater than what? So the answer is from here itself. So when I say this term is becoming 0, that is there are two options and I'm saying maximum is 0. That means this second term is like less than 0, right? So that is when the first term will become 0. The loss will become 0 if this second term, that is d plus minus d minus plus epsilon, is lesser than 0, right? So the condition becomes what? This condition is equivalent to what? uh, d minus minus d plus is greater than epsilon. That is this, it is how far my negative sample distance minus my positive sample distance is greater than epsilon. So that is if I put them together like this. So if this is my positive, okay, I'm very bad at drawing these things. So if this is my positive anchored, this is my negative, so this is d plus and then this is d minus, right? So d minus, this thing should be greater than epsilon. That means they're far enough apart. So if they're far enough apart, then I don't have to consider them in the objective. It's already far enough. That is why loss becomes 0. But if it is lesser, then this d minus is, I mean this epsilon is lesser than the distance between d minus minus d plus. If it is lesser than epsilon, that means they're still close. That is why I still want the loss term. So what would my loss term be? The loss term is exactly this term, d plus minus d minus plus epsilon. This becomes the loss. So whenever this distance between the both become greater than epsilon, then I don't need any loss. So that's how this is, the logic is defined. Is that clear? Like any doubts? It might look messy, but is the logic clear? This is how margin losses are defined anytime. Functions are applied on the logits we get out of CNN, not logits. It's all done on features. So we do not have a classifier layer here. It is only on the feature extractor. So this feature extractor, so this f of x is output of feature extractor, not logits. That's a very good and important question. It's not logits. Any distance based metric and objective you use, it's always done in feature space, right? Because that is where, in geometrically, that is where your feature vector is, and you're calculating distances and optimizing those distances. Logits are some interpretations, right? Like scores you are evaluating, they are not real um, interpretable numbers in the 3D space, not 3D, in the high dimensional space. So this f of x could be like what? Some 1024 dimensional vectors, 512 dimension vectors, that kind of things. It doesn't matter how many number of classes you have. It depends on the architecture. In my last layer of the architecture could be a 512 dimensional feature space, then it would be so everything we will be calculating in that space. Is that clear? So whenever you are using this metric, these kind of metrics, so even if you're using a CNN, which you're, and what would we usually take a pre-trained CNN and start from there, right? Like say I'll load a ResNet and then I'll put this. So you have to make sure you don't use that last layer. If you just, because by default the network architecture would include all of them, right? Because they're like ImageNet pre-trained CNNs. So the last fully connected layer would be the classifier, 1000 class classifier type, right? So if you are going to use these distance metrics, you have to make sure that you remove that or don't use it in your forward pass. Like modify your function so that you don't use the forward pass, get the features, and then write these equations in code. Is that clear? So yeah, here I discussed about supervised classification, right? That is where I have these IDs associated with them. So these were all contrastive objectives, but still, like the face recognition example I discussed, they still have labels, right? Or even in this case, when I'm saying positive and negative, so positives I would pick like the same person's another image if it's like for my, if the image is a sample of mine, then I'll pick another image of mine and choose that as positive and say another person, my friend's image as a negative, and do. But yeah, now let's just see how the objectives remain the same, but what positives and negatives differ when we move on to what we call as self-supervised learning. So what is self-supervised learning? So you have seen supervised learning, unsupervised learning, and then this is a different stream called self-supervised learning. So what does this mean? Anyone? So when it we learn a representation which we use for other or later tasks when we generate more data without labels, something like that. Okay. Yeah, you don't use labels, that's why it's self-supervised. If we have labels, then it will just become supervised, right? So we do not have labels, but we still want to learn something. We want to learn good image representation so that I have a network that can still extract something good out of it, which I can use. Yes, that is correct, totally right. So generate more data without labels, that is a wrong statement. Without labels is right, but generate more data, that's not the objective. So by in self-supervised learning, I'm not really generating data. So with whatever data I have, I want to learn a good feature extractor. So if I learn a good feature extractor that can understand very lots of low level features well, it can see, I mean, even us humans, right? It's not like as soon why we are like good feature extractors, not like we always know what means what. So the label comes after someone saying what that means, but understanding the information we can still do very naturally, right? So that's the self supervision part. So how do we do that? Like if there is no labels, then how do we learn, or what do we even learn, right? What is the task? So usually our loss objectives are always have labels, and I want to increase the score for a particular class, minimize this distance, that distance, and so on. But here we don't even have a task, we just have lots of data. Like I give you some 1 million images. What is the best you can do with it? I don't give you any labels, like, but how do I use those 1 million images to learn something new? I still need a loss, right? I still need an objective so that I learn the network. So what objectives? How would those are? Yeah. So what is the task which I'm creating here, so that I define an objective and then learn something? There are no real tasks, right? We have to imagine tasks here. Grouping similar features. Grouping. What is similar features? We don't even know, right? If I don't have labels, then what do I call as similar? We don't know what is similar or not. The goal is to learn similar looking things should have similar features, but for real, we don't really know beforehand. Similar pattern. Similar pattern between what? You're only telling the object, like, mm, yeah, similar pattern between what? Between two images, between, that's the important part, right? What goes here in my loss? So in my loss, what inputs go? So fine, objective is to make something similar. Asking the model itself to predict. To predict what? Predict what? Similar of what? Yeah, we want to make the model predict something. We want to make something similar. But what is it that we want to make something similar? How many of you have watched this week's lecture? Ask the model to predict itself between two objects. So what are those two objects? So data points. How would I choose these data points, right? Like, so I have random data collected from the internet, and I want to make, I can't make anything similar to anything, right? Clustering, all these are, yeah, you guys are picking words and saying them out, but how exactly are you using them, right? That's the important part. These are like fundamental elements of a learning algorithm: data, objective, similarity, grouping, clustering, everything. But like designing the algorithm is the main part, right? Like this applies to any question I ask you. You can say all these things. So data points. Now say I have given you 1 million images. So I randomly pick two images from them, and I make them similar, like make those two features similar. What would happen if I do that? Is that what I'm trying to say? Would I earn anything by making two random images similar? In that sense, I will create lots of combinations, lots of pairs. I make two of them similar, two of them far. But what happens at the end if I randomly picking? Depends on our target, what we want to do. There is no target here, right? That's why it's called self-supervised. We don't have targets here. Like there are no labels, there is no objective. The only objective is to learn a good feature extractor. So here, let's just take this um, face recognition example only, right? Where I said I have 1,000 images, right? 1,000 images, but I don't have labels, suppose, all these IDs. So I just have 1,000 images. I can use the exact this triplet loss or this contrastive objective, same. So if I don't know the labels, how do I pick positives and negatives? So so I'm telling you what the objective is, but what goes into that? What becomes a positive? What becomes a negative? That's the important one, right? Take a image, make the image and its augmentations which we create, and all others are dissimilar, right? Yeah, so when I'm saying two things have to be similar, only if we expect it to be similar, we should make it similar, right? I can't pick two images and make them similar just like that randomly from that 1 million images. I can't randomly be picking two images and making them similar. At the end, what would network learn? It's just garbage, right? It'll just put one whole cluster of everything at one place. If I just do that, there is no meaning to that. Yeah, to take an image, we are like synthesizing a task, that is creating a task of so how do we create this positives? Predict what, similar what, right? Contrastive learning, yes, these are all things which you do, but how exactly to do is the question, right? So the loss is exactly the same, nothing changes. This whole thing is same. So this remains exactly the same even in self-supervised. Just that you have to define what is XP, what is XA, what is XP, what is XN. I have 1000 images. So from this we have to create a task so that I can get this XA, XP, XN and put this loss. So fine, I pick one image XA. So as it's positive, I don't know its label, I just pass it to an augmentation of XA. So that is my other sample. So this becomes my positive. So what do I mean by augment? Can someone name me a few augmentations? XN, I'll pick some other sample. Something else such that xi is not equal to xa. So any of them from that. So this is one image from the other 999 images. I pick a negative. Color, noise, rotate, crop, flip. Yeah. So by doing these transformations, I am not changing the identity, right? So these augmentations are identity preserving in nature. This is very important. Okay, so like suppose I have digits data like MNIST. Okay, so that is the data set I have given you. So what are all the valid augmentations on MNIST? So you guys named um, crop, flip, rotate, colorization, noise, adding noise. So and yeah, this is also an important thing, right? So what are valid augmentations for MNIST dataset if I have to use them? So I don't have the labels and all, but I just know by looking at them I know it has numbers. So in that case, what all can I do to say that, oh, this is, if so it's like the augmentation is it should be such that even if suppose I label them, the label should remain the same, like label for XA and the augmentation of XA would be same. So that is how augmentation should be defined. Translation, okay, translation is also another type. Yeah. So yeah, tell me, is cropping a valid augmentation for MNIST? Tell me yes or no. You can type it on in the chat for each. I'll name the augmentation. You tell me yes or no. No. Why? Okay. Say I crop it such that it's a center crop, so that I don't lose the number. In such a case. As long as I don't do dramatic crops, it is valid, right? Yeah. What about flipping? Flipping, yeah. Rotate. Yes. Are you sure? No, 9 looks like 6. So actually not even flipping, right? If you flip, the number digits don't look the same. Although it will not uh, overlap with an existing one, it still doesn't have its meaning, right? So not even flipping. Like 7 is this, but then its flipped image would look like this. But knowing that it's numbers, it does not have meaning, right? But flipping in general can be used for other images. Rotating, no, because yeah, 6 and 9 will be the same. Colorization, I just changed the RGB values like up and down a bit. What would happen? If I'm only caring about the number, I can do it, right? Noise, adding Gaussian noise, suppose. Yes or no? Translation, obviously a reasonable amount. Like, so all of this, like translation, crop, you do something like slight shifts only, right? Mildly, so that you don't really lose out on the whole content. In such a case, yes or no? Yeah. So these are all valid augmentations. For general images, yeah, you can even do flip and all. Like if it's like flowers, animals, and all, right? You can just flip them. Even rotate should work because yeah, you can still recognize what that animal is, right? We humans can. So anything identity preserving, as long as it is that, like, the semantic meaning should be intact. So yeah, although for most cases you can use all of them, but it is still like you should put at least some 1% thought into noise, seeing intuitively if the augmentations make sense. Anyway, so yeah, as I said, I have an image. So its positive is what? An augmentation of that image, and its negative is some other image x prime, which belongs to, it's like the other one of the other images, leftover images. And then what is my objective? So x and distance between this I want to reduce, and then distance between this and minus I want to increase. Anyway, like there are different objectives you can, but at the end that's the logic, right? Minimizing this distance, maximizing then distance with the negative. So yeah, where did I start this? Okay, so yeah, this is one way of okay. So this is actually called as SimCLR, which is a very common thing. So what are the other? So this is one task, right? One task where we have defined what augmentations are, what positives mean, what negatives mean, so on. So what are other self-supervised? So this is a task which we defined, right? Ourselves. Other self-supervised tasks which you can use. So after training in this way, you have learned a network which has still understood some structure in the images, so that if you use that and then do some simple fine tuning for a new task, it could easily converge because it's already learned a lot about what images mean. So there are several such tasks. One is the contrastive objective. So name me a few. So what are the tasks which you can synthesize without needing labels? It's like creating virtual labels. Like, can I create virtual labels and ask the model to learn something from pure images, not manually annotated data? Image in painting. Yeah. What is image in painting? Filling up missing or corrupted regions of an image. Yeah. So I pick an image, then what do? I mask out some region, like this part. I just make it black, suppose. Like make it black. And then I give this as an input to the network. So this is usually done in an encoder decoder fashion. Encoder, decoder. Then this has to predict something here. So what was the objective? What would the objective be here? So this is my mask. So wherever my mask is there, mask equal to 0, suppose, so that I have like blacked out pixels at all those regions. What am I doing? This is input image, this is predicted ones. So x cap minus x whole square, right? Sum of all these pixels. Summation over all pixels. But the loss is applied only where it is masked. That is, here I'm saying the mask is black, so I've chosen m equal to 0, predicting the unknown part of an image by seeing the other part. So it's like, if I know, how can we learn to input an image if we only have corrupted or blanked out images and no ground truth images? You're not starting with corrupted or blank out. You have the real image. Like this is your image. So this is x cap. Okay, yeah, this is so this is my input. So this is my masked image, suppose. So I give the masked image as input, but this objective is learned with the original image. So the ground truth becomes your original image, right? So ground truth is equal to original image itself. If some other setting, if you have this problem, how to handle it? If you only have corrupted or blanked out images and no ground truth images. So that sort of becomes like a denoising problem. Corrupted images to denoised images. Like blanked out ones you can't just fill without any knowledge. Unless your network already has seen something, it can't, right? I can't like just using blanked out images making it to hallucinate. That's what I'm asking the network to do, right? But even to do that, I still have to make it learn something. Unless it's a foundational model which already knows how images are, from scratch you can't just make something work from blanked out images. But there are these classical methods for image restoration. Yeah, I have forgotten all those things right now. Which, like, where it without using ground truth also, right? Like image denoising methods are there, which assumes like how a natural image should be, and try to, example, in night road scenes the vehicles are covered by glare. Can we do some inpainting there? Yeah, you can use inpainting to do that, but your model should have learned how to do inpainting beforehand, right? If I have a model which has trained to do inpainting, I can use it, right? My input images do come as so this is all preparation part, right? This is not like inferencing part. All this is training part, what we're discussing now. So for training you need like real images where I can patch out something, mask out something and train. Once you have done this part, if then you have the inpainting model. So obviously when your test image comes with where some regions are masked out, then you can inpaint on them. Is that clear? So is this objective clear, how you write the inpainting objective to everyone? So here at the end, so we do not um, have manually labeled ground truth data, but still we do have ground truth and input data here, right? So these masks can be randomly synthesized, right? I just randomly select a region and mask it out, but I still have my true image. Well, because I'm randomly doing creating this mask through my code, I do have where the mask is, its location. I can do all of this. So I'm like synthesizing this task. So these are like virtual tasks. Okay, image and painting done. What else? Any other task? Masking. This is masking, right? Masking and inpainting are the same thing. You guys should be aware of what. I mean, this is fine, but as far as I can say, you guys are very well aware of all this terminology. You know these words, but when are the words the same, different? The underlying meaning of them also you should know. We just discussed what inpainting means, and masking is the exact same thing. So if I ask you the question, what is masking, what would you say? You would have to say the exact same thing, right? Yeah, any other task? If you have watched this week's lecture, you should know, right? There are two at least on top of my head. Image coloration. Okay, what is image coloration? Grayscale to RGB conversion. Oh. Mm, yeah, that could be one task, although I have not heard of it. Mm, but I don't know if it can understand the details present in that image by this task of coloration. Because like I don't need to understand whether it's a cat or a dog to color it, maybe, right? So as long as it understands the palette, like as these are the kind of colors a cat, like something like this looks like, maybe, yeah, but still, like finer details, I don't think it would be able to learn using this, as in understanding lines and structures, like those kind of things. This is a very low level task, right? It should, like, my guess is that it should be able to infer what is there in the image to make this task. Face recognition. How can you do face recognition if I don't even give you images of faces? I just said I'll give you like 1 million images from the internet. There are no faces, or I mean, faces can be there, but you don't know for sure, right? Order, like solving puzzles. Yeah, jigsaw puzzles. Solving jigsaw puzzles is one thing. So here I shuffle the patches of the images. So say I have 1 2 3 4 5 6 7 8 9. So this is my ground, this will become my ground truth image, and then I shuffle them. Say 5 9 8 2 1 3 4 7 6. So I shuffle them. So this is my this would become my input image to my network. So what would I predict here? What should my output be? Yeah, order of the grid. Matching of the pixels. Relationship between pieces. Yeah, relationship between pieces. Yeah, if I have like indices for these 0 1 2 3 4 5 6 7 8, then I know my 1 is at 4th position, right? So the first prediction, like for the order of the to predict the order of the grid, it should be 4, and then 2 is where 2 is at third, 0 1 2, the third index, then it would be 3, and then 3 is at 5th index, 4 3 5. Yeah, so can someone complete this for me? So where do I have 4? I have it at 6. Where do I have 5? I have it at 0. Where do I have 6? I have it at 8. And then 7, I have it at 7. 8 is there at 2. 9 is there at 1. So this can be like the order of the grid which I want to pick, or even the relationship, it can be modeled. So by doing this, what are we doing? Like so it should understand the structure in the image by doing this, right? Because I'm messing up the patches, and I'm trying to solve that messed up patches into bring some structure. So it's like discover structure. So it's like globally it will understand what is present in the image by solving this, right? It should decode the global structure. The image from a puzzled grid. So this is also a task which we are synthesizing, right? These puzzles can be randomly created. I randomly create and mess this up and do it. So I'm synthesizing this. So there's one other thing which is, yeah, quite famous and commonly used. Anything else you can think of? Not like I can think of also. I know that why I'm asking. there's this paper called ROTNET or Rotation Prediction Network. So this is also synthesized task, right? Rotation prediction. So we have an original image, and then from this I can create 90 degree, 180 degree, 70 degree kind of augmentations, right? Like 90 degree rotation, then 180 degree rotation, 270 degree rotation, these things. And then for these labels I can name them. Yeah, so one can be 0 degree where it is as it is. So I can name these labels. Y is 0, y is 1, y is 2, y is 3, like 4 classes, 4 class classification for 4 degrees of rotation. So this is like a I have a so I pass my input image, like the rotated image. So say this is the rotated image. I pass it through the network, and then I have a 4 class classifier, 1 2 3 4. So here I have a 4 class classifier, and then I predict something. So I predict which of these classes it belongs to. So and then I train the network, so it understands which rotation it is. So yeah, these things kind of it's a synthesized task. You learn, you extract features so that you understand some structure in the images. But it turns out this rotation prediction actually works really well. Like if there are some features that don't really get activated in one rotation, it could be more activated in some other rotation, and overall it learns what the underlying structure means, something like that. Empirically people have used it in several tasks, that this self-supervised objective with other tasks and all, or tune it for other new tasks where rotation prediction where it's initially trained using rotation prediction. Yeah, okay then. What is that to discuss? Okay, it's all about contrastive learning. Then there were some discussions on vision language models, right? So yeah, when we say vision language or multimodal models, like we have two different modalities. So all this while we have been dealing with just images, right? Even all the self-supervised objectives were all with just images. I have image data and I do something. So here we have two modalities, and we want to learn something by matching two modalities, because that's how we humans perceive data, right? Like not always just through one modality but through different modalities. So there's this one very famous model called CLIP, which stands for contrastive language image pre-training. So as the name says, it is trained using contrastive learning objective between language and image, and it's a pre-training framework because it's completely done in a self-supervised manner, not somewhat self-supervised, because it's not really humanly annotated with humans. Self-supervised between two modalities, contrasting between two modalities more like. So this is trained on lots of web scrape data, like millions of it. I don't know the exact number, I don't remember it, but millions of web scrape data where we have an image and a corresponding caption with it, right? Lots of images on the internet have some caption associated with it. So we have images and captions. So like there's an so it's like trained on pairs of image and caption. So the image goes through a um, image encoder, and you get image feature of the image, and then you have a caption. So this goes through a text encoder, and then you get a feature for the text, and then you contrast between them. You maximize what is this, you make these two similar, that is image cosine similarity. So it usually they use cosine similarity function, or yeah, this is dot product, and so this is cosine similarity, right? So this symbol refers to dot product. Dot product divided by its norm is actually cosine similarity between Fi and Ft. So by doing this, what would happen? It would learn a high dimensional space where image and text term is matched, right, with this objective. So what, fine, so it is pre-trained in this fashion, it's learned on lots of data. But what is the advantage of, like, compared to just image based pre-training versus this? um, do I have any straight away advantage from this pre-trained model? Any guess? I mean, without doing anything, I just use the clip model as it is. Can I solve some tasks directly? So in self-supervised, like when you train using all these, right, like rotation net, blah blah blah, just these tasks don't give us anything, right? Like it's learned good feature extractor, but I need to use those feature extractors to tune on something else. Like fine, I could have had a rotation prediction network, then I have a classification task or a segmentation task, so I add some layers to it, and then I train it for classification or segmentation, then I have a network ready. But there is that extra step required, right, to tune it for something else, for like even for classification for that matter. I need to add that extra layer, learn something. So but from this vision language model pre-training in this fashion, where I've used the image and text together, is there any straight away advantage to do any task? Image captioning, uh not really, because this does not generate images, right? Captioning is a generative task, this is not a generative model. Image captions can be used, but how do you use the captions? Like, can you use it in any intelligent manner to do any task? But yeah, it doesn't generate captions, so it's not like I give an image, clip doesn't give out a caption to me. Classifying new or unseen data, yeah, it can be used as zero shot classifiers. How can it be used as zero shot classifier is, so suppose I want to test it on ImageNet data, suppose, to test on ImageNet 1000 classes. So I can compute a classifier for free, like classifier obtained for free. Why do I say free? Using the text modality. So what do I do is, I'd write a classifier as a photo of a cat, a photo of a dog, photo of a table, blah blah blah, like this, of a pen, blah blah blah. So I can erase whatever are my classes of interest, so 1000 classes. So I get, so when I say ImageNet 1000 classes, I obviously know the names of these, right? Names of these classes. So as long as I know the names of these classes, I can create classifiers of them. 1000 names. Use them, and then I pass it through the text encoder, and then I get, so I say the text encoder embeds it into a 512 dimension, then I would get what, 1000 cross 512 dimension vector, one classifier per class. So this becomes my classifier, C1000. So now I have a test image. So this is a one-time task, like I define the classes of interest, so this is a one-time computation only to get the classifier. So now I have a test image and I want to identify which of this class it belongs to. Then I pass this image to the image encoder, and then I get the image feature, and then what do? I compare it. So I have all this, right? So let's just say C1, C2, blah 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 to C1000. Okay, leave this C1000. So what do? If I have to predict which class it is, I would do argmin over, so compute the cosine similarity. Okay, I should do cosine, not write this cosine similarity because it's trained using cosine similarity, and that's a logical metric, right? Cosine similarity of the image, and if not if what, let's just say Cj for less confusion, j belonging to 1 to 1000. So I get 1000 numbers, like 1000 similarity values. Oh no, yeah, this is wrong, right? It's not minimum, it should be max because it's a similarity metric, it's not distance metric. So the one it matches with the highest, and then I give that as the prediction. So you can get a classifiers for free. This required no fine tuning, nothing. I just use the clip retrain model, like I know the names of classes I am interested in, so I get the classifier and I'm done. Yeah, so clip is one model, and then there are all these blip versions which are like captioning model, all of that I think. But all of them are trained on unsupervised data, just using like image caption pairs from web scrapped from the web. Okay, let me. There are a few questions for like this week. I'll discuss that maybe, and then we can end the class. You can see my screen, right? Yeah, so in the context of self supervised learning, contrastive learning has been widely used for representation learning. Which of the following statements is not true about contrastive learning and its relationship to self supervision? Contrastive learning aims to maximize agreement between differently augmented views of the same data sample while minimizing agreement between views of the different samples. Is this true? While minimizing view between, why is it not true? In a self supervised framework. Couldn't see. Is everyone able to see it? Or is it just. It's, it's true, right? I mean, I want the image and its augmented view to be uh, to agree with each other. And for other sample, I treat them as negatives and reduce the distance. So the first one is true. What about the second one? In contrastive learning, negative pairs are typically formed by using artificially generated noise samples rather than real data points to improve robustness to outliers. Is this true? How are negatives chosen based on what we discussed? All the other images in the data set, right? So we're not synthesizing them, so it is false, yes. Okay. What about the third one? One challenge in contrastive learning is the requirement of large batch sizes or memory banks to ensure a sufficient number of negative samples, without which the learned representations may collapse. Okay, we didn't discuss this, but this is actually true that it does require large batch sizes. Its effectiveness is proved with it's learned better with higher batch sizes. What about the last one? Contrastive learning requires labeled data to generate positive and negative pairs, as the labels help differentiate between classes and ensure proper supervision during training. Is this true? No, right? I'm not relying on labels to differentiate them. I'm choosing positives as augmentations, negatives as other samples. Several pretext tasks in self-supervised learning use specific augmentations like jigsaw puzzles, rotation prediction, and colorization. These tasks help the model learn useful representations without labeled data. Which of the statements about these pretext tasks and augmentations is not true? Okay, is the first one true? First one is true, right? Because that's the task. I shuffle them and I want to predict its correct order of patches. Rotation prediction as an augmentation teaches the model to recognize object orientation by rotating the image randomly by 0, 90, 180, or 270 and training the model to predict the rotation angle, which leads to learning orientation invariant features. Is this true? It is true, right? Yeah. Yeah, it learns rotation, orientation, invariant features by this kind of training. Pretext tasks like jigsaw and rotation are designed to improve performance on image classification but are generally ineffective when transferred to tasks like object detection or semantic segmentation. What is this, true or false? False. Yeah, it's a representation learning task where the goal is to learn good feature extractor, and it can be used in any of these tasks, right? Like there's nothing to say that that is not good. It can't be transferred to object detection. It still learn good features which can be leveraged to tasks like object detection and semantic segmentation. What about the last one? Is the last option right? Okay, let's see. Look at the first statement, right? They've said it's considered to be invariant to local structure distortions. Do you think it would be invariant to local structure distortions? As in, in the sense that, so I have an image and then I shuffle them and pass it. That's like one sample, and then I have another one where I slightly distort the image, like shift it or something like that, and then I create something and pass it. So it's not like my objective doesn't really enforce both those features to be the same. I intend to correct and recover my global structure. So I think that it can understand the global structure, but it's not really robust to local structure distortions. It's not like shifted image versus the real image has the exact same representation. Such. So in that sense, it can understand the global structure, so it can infer what is there in the image, but it can't really understand the fine-grained details of the image. I think because that's not the task. The task is to recover the global structure. So the last one is false. Does that make sense?
Now I have a confusion in the last section.
Yeah, tell me.
So if we even rotate the image a little and then task, maybe the order may be different, but the order in the original image and this may be different.
Yes,
But it
yes.
still tries to construct, give the order based on the whatever the distorted image we have given. So
Yeah.
I think it should be true.
Yeah, it will still solve the task and it will recover the order. That I agree. But when it comes to what here, when they're saying it preserves fine grained details of the image, so making the order same, so it can learn to make the order same. That means it can recover what the global structure of the image is, right? But it might not be understanding what fine grained details are there in the image. That is what I'm saying in that sense.
Yes, understood.
from this perspective. Obviously it's still learning something, and but the focus is more on the how the task is defined is that it understands the global structure, right? But suppose if I am in contrastive learning, to contrast this jigsaw task with contrastive learning, where I'm creating augmentations, right? Where I'm augmenting, like flipping, translating, all these things. So I'm creating these local perturbations in the image. And then, so here I'm actually disrupting even the fine grained details, right? When I'm messing up with its color, distort, adding noise, and all that, I am messing up with the fine grained details of the image. And um, and I'm training it so that my original image and this perturbed image have same feature, right? Like they match in the similarity, I mean in the feature space. So in contrastive learning, using contrastive learning objective, so I'm ensuring that it is robust to these local perturbations, and can yeah, know the fine grained details in that sense. But jigsaw task, it can recover the global structure. So it's fine if the words are not this, but I hope you got the intuition at least. So is the first one true here for SimCLR? We just discussed this, right? Is the first one true? It may fail in data sets like MNIST, yeah, that is right. But that apart in general. Yeah, so these random cropping, flipping, distortion as usually work with most data sets, right? Yeah, except for things like MNIST maybe. So yeah, first one is true. And what about the second one? So what do you think second one does? Is it true or false? False. Yeah, false. Yeah, false is right. Because if we use very strong augmentations, right, like heavily blurred noise, that like I'm disrupting that image way too much, and that is not really synthesizing any real distortions also, right? So in such cases I'm like giving really hard images which I'm like pushing the features really far apart and asking them to come close. So using very strong augmentations is not really beneficial to learn downstream tasks. I will use only mildest augmentations for as positives, right? I don't want to use heavily blurred image as a positive for my current image. What about the third point? The combination of augmentations in SimCLR is designed to ensure that the views maintain enough semantic content to be considered positive pairs while still being sufficiently different to avoid trivial solutions. Is this right? True, yeah. That's what we want, mild perturbation, so that they're slightly apart but then they're still close, yeah, but not identical. So, yeah, it is true. What about the last option? SimCLR uses augmentations like random cropping and jittering to artificially inflate the size of the dataset, making it possible to train with fewer samples while maintaining similar performance. So, is this the objective, like the goal of using augmentations in SimCLR? False, right? Yeah. Yeah, it's not used to increase the size of dataset or like learn with fewer samples. That's not the goal at all. It's to create these positives and negatives so that I can use them for okay. In SimCLR model, a batch contains 512 images, and each image generates two augmented views. Assume each augmented view has exactly one positive pair. Calculate the total number of positive pairs. Each augmented view has exactly one positive pair. Calculate the total number of positive pairs and negative pairs in the batch. So they have said that for each image there is exactly one positive pair, which is those two augmented views, right? So for every image we have one pair. That's what they have said. So at the end we totally have n pairs. So the total number of positive pairs is 512. And what about the negative pairs? So for every image now we have, for every image we have, it's one augmented version and another augmented one, so there are two images per like per element whatever. And so in that, so totally how many images we have? 512 images and the augmented one, so totally there are 1024 images, right? So how many negative pairs would we have? We would have, except for the for its true positive pair, rest all are negatives, right? So there will be 2n minus 2 pairs. Okay. So Clip has demonstrated strong zero-shot performance on a variety of tasks by learning joint representations of images and text. Which of the following statements about Clip's architecture, training strategy, and generalization abilities are true? First one is it uses dot product of image and text embeddings to compute similarities, which are then normalized by softmax function to align positive image text pairs. So, do they, based on what we discussed, do they use dot product or any other measure? Is the first one right? False, right? We use what? Cosine similarity as a metric. Is the similarity metric, not dot product. I think they don't use softmax. Yeah, they don't use softmax. Yeah, it's just maximizing the cosine similarity. That's all. What is the second one? Clip uses two separate encoders, one for images and one for text, allowing both modalities to be projected onto the same latent space, where cosine similarity is used to match corresponding pairs during contrastive training. Is this right? Yes, yeah. Yeah, that's exactly what Clip does. So, what about the third one? One of the main reasons Clip performs well on zero shot tasks is due to its training on a wide variety of image text pairs from diverse sources, enabling the model to learn general representations that are transferable across tasks without fine tuning. Is this true? It's true, right? Mm, what about the last one? Clip's zero shot capabilities are primarily limited to object classification tasks, and its performance on more complex tasks like image captioning and visual question answering requires additional fine tuning. Okay, why is it false? Okay, we have two answers, false and true. Can you guys, actually this is a very ill written statement, I would say, but let me know what your views are. Why are you saying yes, why are you saying false? Let's see it as a discussion rather than as a binary answer here. So can I straight away use Clip to do image captioning and VQA? So Clip is just trained on to what, if I pass an image, I pass a text, I get some embeddings and I can compare them. But can I directly use it to do image captioning? It can have the capabilities to do it, but can it be done in an off the shelf manner? Like, how would you ask Clip to do image captioning? Is that feasible directly without any extra step? I mean, we discussed that Clip doesn't generate any caption, right? So it's not a generative model. It can't directly generate a caption. Even VQA is a generative model, right? It needs to answer it. So you need something more. Like, it can understand what language means, but that doesn't mean that it can give out captions or answer questions on it, right? So you could use Clip as a module and then learn something more or tune it or with in combination with a different model so that you can do these different tasks. But like straight away, it's so we can't really say it's limited to object classification. So it can do more than object classification, but not in a zero shot manner. So it needs something more to be done to be used in tasks like captioning. Dot product and cosine similarity are same, right? No, no. Dot product does not ensure it norm of them is one, right? You take two vectors, dot product is just combining, multiplying them and summing them. Cosine similarity is done on unit vectors. It cosine similarity gives angle, dot product gives similarity. So dot product can be greater than 1. Cosine similarity will always be in the range -1 to 1. So you norm the vectors and then do dot product, you get cosine similarity. So directly dot product you don't get good measures, because if you just make a vector, so there are like two vectors, you just increase the length of one vector and multiply it with the other one. So even if something is very far apart, just because of the magnitude of it, you can get high similarity, right? Which is not necessarily true. So cosine similarity is a better metric, not dot product. Blip. So Blip and Blip 2 models are advanced multimodal vision language models that combine vision and language pre-training, which are um, which of the following are true? So Blip uses vision language contrastive learning objective to align image and text representation in a shared latent space. But it also incorporates a captioning objective for better language generation. Okay, we didn't discuss this, but yeah, it is true that it incorporates another objective. Yeah. Blip 2 introduces a two-stage training process where the first stage uses frozen image encoder and second stage fine-tunes both image and language encoders to reduce computation and data efficiency. Is this true? It is true, right? Yeah. What about the third one? It relies heavily on manually annotated data and for pre-training. So they don't use noisy web data. Is this true? True?
I think the Blip proposes